Okay, so I'd like to thank the CTQM and of course especially Vaughan for having me here. It's very nice to be in Denmark. I've been in Aarhus before and had a great time there. Then our two countries are in very close battle at the moment for the Olympic gold medal score. New Zealand is winning at the moment by one bronze medal. But in spite of this, I wish you the best of luck tomorrow in the handball match against Croatia, which I intend to watch as a sort of honorary Dane. Anyway, so this, for me, besides trying to entertain you, this is an opportunity for me to actually do some propaganda for Subfactors. So there will be a bit of a sales pitch going on. You don't, of course, have to buy the product, but I think Subfactors have not received perhaps as much coverage as they should have as the origin of a lot of these developments in the last 20 years or so. So I appreciate keenly that most of you probably know nothing whatsoever about subfactors. So I want to start from before the beginning and then try to develop some intuition for what's going on here in this world. So I want to start by asking a question of you. Okay, so there it is. What is the dimension of C plus C? Known as C squared. Okay, well, you know, one's immediate reaction is 2, right? But you know, that wouldn't be the answer if I wouldn't be asking the question if it was 2. So I want to give a sort of more provocative answer. So the obvious next choice, of course, you will all agree, is 4. So we got 2 if we thought of C plus C as a two-dimensional complex vector space. We get 4 if we think of it as a 4-dimensional real vector space. Okay? But here's the answer that I want to propose for today, and this will be the point of entry into the theory of subfactors. Instead of it being 2 or 4, what I propose is 1/2 as the dimension of C plus C. Okay, so what kind of madness leads to this answer? Well, let's go back and review how we got those 2 answers we got already. First of all, we got the answer 2 if it was a vector space over the complex numbers because there were exactly 2 copies of the complex numbers. Right? We got 4 if we thought it was a real vector space because there's exactly 4 independent copies of the complex numbers. So we get 1/2 if we think of it as being a vector space not over those fields but over the 2x2 matrices. Right? Because here's the 2x2 matrices of the complex numbers. We split them in half, we get C2. Okay? So that is the logic according to which we come up with the answer of 1/2, and it's a perfectly fine answer. So that's how I want to get started here with that point of view in mind. Keep that up there as much as possible, so that if you get completely lost with something else, you can come back to this mantra here and think about that. What else it might mean? All right, so we have so obviously C plus C is a module over the 2x2 matrices, and in this philosophy it should obviously have dimension equal to 1/2. So let's get up all of the modules over the 2x2 matrices with their dimensions. So here they are. First of all is 0, and here's the 1/2, and here's the one which is 1. So obviously the modular dimension 1 will be nothing but the 2x2 matrices themselves, which is 1 copy of the 2x2 matrices. And then of course you can start taking direct sums, and you get 3/2, and you get 2. 5/2, and so on. And we'll never stop. And in fact, I suppose you should sort of allow for the possibility of an infinite dimensional module over the 2x2 matrices. So that's the picture. Now we're going to try to make things a little bit more complicated by going from the 2 by 2 matrices to the 4 by 4 matrices. So this is the 2 by 2. Actually, maybe I should even have started here with just C itself. In philosophy, we had nothing there. You had 1 there, you had 2 there, and so on. And you had 3 there. Right. So what about the 4 by 4 matrices? Well, you're always going to have the 0, 1, and the infinity 1. There. What about in between? Well, what's the smallest module over the 4 by 4 matrices? It's C4. Can't get any smaller. And what's its dimension in this philosophy? It's obviously a quarter. Right? So here we have a quarter, and then we have 2 of them, which is a half, and 3/4, and then 1. And 5/4, and 3 halves, and so on, 7/4, and of course infinity. Right, now it should be clear what I'm doing. So we go on to the next one, which will be the 8 by 8 matrices. And you get 0, you get 1/8, you get a quarter, 3/8. I'll squeeze up a bit here. Right? And so you can see that what's going on here, that as you take larger and larger matrix algebras, and you look at these vector spaces over these matrix algebras, they all have their dimensions, and the dimensions are tending to fill out the whole real line from 0 to infinity, with infinity included, the non-negative reals in infinity. Okay? So what do you expect as a limiting procedure? You would expect and hope that there's some object here which is a limit, and of course to obtain it you're going to have to do a little bit of completing, such that this object, which I'm going to call R, with not math R, math B R, but just an ordinary R, and it will have modules whose dimensions will be parameterized completely by R plus union 0 infinity. Okay, so I'm telling you that such an object exists. Since we have to do some completion, we'll expect these modules to not just be perhaps, well, you know, if we want to get the modules by going down there, and these, if you look at these things as vector spaces over the complex numbers, we'll look at them. This one as over the complex numbers is 4, but this one is going to be 8, and so on. So the dimensions as vector space of the complex numbers are increasing. So down here, we will expect to get infinite dimensional vector spaces of the complex numbers, easiest one, Hilbert space. So we're going to expect to get Hilbert spaces. So my assertion is that such an object exists. An algebra which we're thinking of, although it may be a fearsome beast, we're thinking of it very simply as being the scalars of the theory. An algebra such that the vector spaces over this algebra is all positive real numbers and 0 and infinity. Okay, now this beast here goes under the name of the hyperfinite type 2-1 factor. It's realizable, obviously, as algebra operated on Hilbert spaces, and in fact, in all the ways in which it's realizable are parameterized precisely by these real valued dimensions. And before going on, I'd just like to get slightly technical and tell you one way of coming up with these numbers here, besides, you know, if you didn't buy my argument about the dimension of C plus C being a half, if that didn't appeal to you, there is another way to get it, which is quite sort of rigorous. And that is to say, what these numbers represent, a quarter, are actually traces of projections in the algebra. Right? If you took the 4 by 4 matrices, and you took this projection here, and you decided to normalize the trace so the trace of the identity was always equal to 1, to be a common thread of this talk, then the trace of this guy would be a quarter, and the trace of this guy would be a half, and so on. Okay? So another way of saying that there is this continuous dimensionality in this hyperfinite 2-1 factor is to say that there's projections, it has a trace, the trace of the identity is 1, and the trace of the projections takes all values between 0 and 1. Okay, so let's begin our study of R. So it's an algebra, in fact it's a star algebra of operators on the Hilbert space. Has an identity, has a trace. So the trace is required just to satisfy trace of AB with trace of BA. The trace of the identity is equal to 1. And if you take traces of projections, okay, this is the big deal. The set of all traces of projections is the unit interval. Okay? So I hope that I've done everything but give a construction of it. You can construct it actually without too much difficulty by taking some kind of limit of these and completing it, putting on Hilbert space and completing it, and checking that its representation theory on Hilbert spaces is actually given by the real numbers like that. Alright, so there it is. This is this magic object, the hyperfinite type 2-1 factor. Now, there's more adjectives than you could stick at here. Hyperfinite, type the words, type 2-1 factor, right? So I should just say a few words. Factor means that it's simple. If we want the simplest situation, it's simple. As a ring, it's simple, no ideals. Type 2-1 refers to the existence of this trace. So that's this trace for various reasons. As you can guess, there's other ones besides type 2-1. These are the ones we'll be interested in, and they're distinguished by having this trace. And this hyperfinite refers to the fact that we could get it as a limit of finite dimensional things. Okay? So, any questions about this guy? There's lots of other ways to realize it. This is the most immediate and accessible and gives you this idea of a continuous dimension. But I'd like to squander a bit more time and give you another picture of this continuous dimension, which is more continuous from the beginning. So this was sort of discrete things tending to a continuum. I'd like to give you another picture where you get the continuum straight away. And that is the following. So I'm going to construct for you another type 2-1 factor. And I'm going to skip I'm going to be a bit hazy about the completion part as I was here, but we're going to start with the free group on 2 generators. And we're going to take, let's say, the group algebra of it. So this is the group, this is the set of all finite linear combinations of group elements, and I'm going to define a trace from this to the complex numbers by the trace of the sum the trace is simply you just cut off, you just take the coefficient of the identity. That gives a trace. And what you can do is you can complete this algebra in what formally you write exactly the same way you complete this one, and you get a 2-1 factor which is called L of 2. Now it has it's an algebra of operators of the Hilbert space. It has a trace, and the trace of projections is this unit interval. And it's simple as an algebra. You could obviously, you could say, what am I doing taking the free group on 2 generators? Why don't I take any old group? Well, if you take any old group, the property that will get you to be a factor, to make it simple, is simply the infinite conjugacy classes. So if you do this with any group for which every conjugacy class, except of course the identity, is infinite, you'll get a 2-1 factor. Right? Now, as I said, what I want to show you is this continuous dimensionality arising in a completely different way from this limit of finite dimensional things. Immediately it'll be right there. And it arises if you do this example in the case just of Z, which is not infinite conjugacy classes, but you can do the same procedure with Z, and you complete it, and you get the group algebra of Z. Right? This completion goes through Hilbert space, and when we're doing Hilbert space, we're looking at little L2 of Z. Little L2 of Z is the same as capital L2 of the circle. So there's Fourier transform here. And because this group is abelian, Fourier transform works like a charm and allows you to identify this algebra with little capital L infinity with S1, the circle. Right? So everything is very simple in this abelian, sorry, easy in this abelian case. It's not simple, right? This was simple. This one's easy. So it's very simple in this case, easy in this case, and we get L infinity of S1. And I claim that now, and the trace, of course, the trace of the function is nothing but the integral of f in theta normalized. Okay? So now I claim that we can see this continuous dimensionality in a different way. We can simply take the circle, and we take an interval, say, in the circle, and we take the characteristic function of that interval, so 1 on this, 0 everywhere else. That's obviously projection in L infinity. This trace is simply the measure of that interval. Okay, so you can get all values between 0 and 1 if you normalize this thing so that the whole thing is 1. Okay, so we've got two sort of dual ways of seeing this continuous dimension. One is this limiting process, finite dimensional things, and the other is from Fourier transform. By the way, this established it for this example. How do you get it here? Well, you simply take one of these generators of F2 and you've got C of Z embedded in here. So this one, if you like, is this one, but fuzzed up and made very non-abelian by having this other generator. All right, now everything I'm saying, of course, is entirely contained in much more in the papers of Murray and von Neumann through the 30s and 40s, 1930s and 40s. And they really made a magnificent job of it. They discovered this hyperfinite 2-1 factor. They proved a very strong uniqueness result. I could have done this by replacing 2 by 3, for instance. According to their result, you get the same algebra here. Never changes. Provided you have finite dimensional approximation, you always get the same one. And they showed that this one is different. This one here is another 2-1 factor. It formally looks, when you first think about it, you think, well, can't be too many of these guys around having this property. Well, that was surely Murray and von Neumann's hope. They discovered this one, but then they also discovered this one here. They're completely different. There's no kind of finite dimensional approximation in this one. Okay. So that's the theory of 2-1 factors. Since Murray and von Neumann, there's been a large industry producing lots and lots more examples of 2-1 factors having all kinds of good and bad properties. There's been a recent resurgence in that due to Soren Popper, who solved a lot of problems that went back to von Neumann about all of these possible 2-1 factors. So remember, 2-1 factor is one of these algebras with a trace and a symbol. All right, and we have 2 examples. So I think I've covered that, and I hope that everyone is still with me. And I've given you some intuition about what this continuous dimensionality of Murray and von Neumann was. And it was kind of a big deal. One other word that I see here is amenability. What von Neumann, one of his things that he discovered is to figure out what is the difference between these two 2-1 factors was a concept of amenable groups, and that ended up playing a huge role in the theory which I'm going to be talking about. All right, because I want to get on, of course, to subfactors. So we're in this world now of 2-1 facts, so the main thing we've got going on is a trace. So it's obvious with the way I've presented the subject, it should be a fairly natural question to think about subfactors. So I'm going to use the letter M for a 2-1 factor and perversely N, capital N, for a subfactor of it. Another 2-1 factor contained in it, and just in case you're worried, they have the same identity. Same identity. All right. So why is that an immediate thing that you might immediately think about studying? Well, the answer, of course, is if we're thinking of these things as coefficient, as fields, they're not. There are lots of projections, which are zero divisors, but in terms of dimension, they have nice properties of fields. Think of these things as fields, and what are we studying here? We're studying Galois theory. Okay, so subfactors, another way of, the best way of motivating probably is this sort of quantum or non-commutative Galois theory in this infinite dimensional setting. And what I'm going to try to convince you of in the next 5 minutes is that it's better than Galois theory. Okay? See, in windsurfing and kiteboarding, we have this, everyone says, better than sex, right? And there's some, some evidence, some reasons for saying this. Well, this is the same thing. Better than Galois theory. Galois theory is really good. This is better. Okay, so why do I make this claim? Well, the first thing is I'm going to be mostly concerned with this hyperfinite case. And I want to just tell you a result about this hyperfinite case. And this result is basically due to Kohn. It was actually my thesis, but I was just taking a result that he had and generalizing it. And the result is the following. It is that if you have a finite group, okay, so the stuff of Galois theory, then up to automorphism, up to conjugacy by automorphisms, in other words, up to just a coordinate change, there's a unique way in which this group acts on the hyperfinite 2-1 factor. Acts in a unique way. On the hyperfinite 2-1 factor. Now, to be technically correct, I have to tell you that all of the automorphisms are outer. None of them are allowed to be inner. That's the thing that makes it unique. Otherwise, you can fiddle around, do sort of things. But if it's outer, and it's only one way in which it can be done. So this is sort of amazing. The immediate thing, so you have a group of automorphisms, and just borrowing from Galois theory, you could look at the fixed points, and you would get a subfactor in that way, right? Just look at the fixed points. Well, I assert that this is actually also a factor. It's not very hard because of this outer property. Well, Galois theory works really nicely, and just follow your nose with finite fields, and you'll find that you can reconstruct the group from this. If you just forget that it came from a group, just take this subfactor, that actually gives you G. So if you hadn't discovered finite groups before you discovered subfactors, then they would be right there. So you just look at these ones, you can easily characterize them, and you would say, aha, there's these interesting things with elements that can be composed and so on and so forth. Okay. But there's this uniqueness result. There's no more. So in other words, this data here, this subfactor, I want to remove this, and let's call it 0. That data is completely equivalent to a finite group. Completely equivalent. There's no difference between giving yourself the finite group and giving yourself this subfactor. Now that's better than Galois theory, right? Because Galois theory, you would get the finite groups, but you're going to have to muck around with the field and so on to get it, right? I mean, it's still open whether you can get every finite group as a Galois group for extension of the rationals. At least it was last time I came into contact with that word, will. So, and if you have a given field, then there's lots of different ways in which you can get this group G. Here it's different, it's just superb, you don't see anything. All you see given the subfactor is the group, you see nothing else. Ultimately, because of the strong uniqueness result of Neumann, says there is only one of these guys. It was souped up by Vaughan and myself you can say that only one of them has G module, with action of G. So, fantastic. So now there's some real motivation. So you say, well, we've got all the finite groups, let's look at an arbitrary subfactor. So we'll forget this one came from a group, and what can you say about it? And so that's my motivation, the better than Galois theory motivation for looking at subfactors. Alright? So, I haven't told you much about 2-1 factors, but I've told you enough that you can take the next step, which is what's the first thing you would do if you had a field extension in Galois theory? If you didn't know anything, but one was a vector space over the other. So you could define the degree of the extension, or the index of the subfield. You could define this number, which would be the dimension measured by m of n. Okay? You could define that. Now this makes perfect sense here. If n and m are fields, then that's just the dimension of a vector space. N and m here are 2-1 factors. There's a little bit of mucking around about Hilbert space, but it's not very serious. In fact, you don't even need to do it if you know when I said that you had to take Hilbert space here, that was overkill. There's a lot of other ways to take these limit things. So this is a perfectly fine number. Okay? Perfectly fine number. It's a perfectly fine real number. Okay? Because according to Murray and von Neumann's great big deal at the beginning, the dimensions of modules or vector spaces over these 2-1 factors are real numbers. Okay, so, well, there's some numbers that are immediately ruled out, right? M is bigger than n, so the number's got to be at least 1. So it's greater than or equal to 1. It could certainly be infinity. There's easy examples to make it infinity. So then the question becomes, well, what else is it? So the sort of, let me give you a few examples and then we'll try to get some intuition. What are the real numbers? Okay, so let's look at the examples we've got. I've only given you one, right? The only one that I gave you was, well, I haven't even given you what this, but anyway. What's the degree of the extension when you take a fixed point algebra for a finite group acting by automorphisms? Well, there's only one guess, right? And you know, you'd be really stupid not to guess it. So by proof by, was it? Brute force by intimidation. The answer is, you're all saying it, I'm sure, the answer is that. So that's true, and it's not very hard to prove. Now, here's another example, which is in a sense, which is actually even easier than this one. Given one of these 2-1 factors, there's a very simple operation you can do on them. You can take the 2x2 matrices over them. That's another 2-1 factor. It obviously has a trace here. So you can take the 2x2 matrices and write it. And no one gets confused. Now that contains R itself as the diagonal submatrices. So this, yeah. So let me get the picture up again. We're back to the 2x2 matrices, which have served us very well. A, B, C, D. So it's the symbol of all these things where A, B, C, and D are in R. Remember, this is our how to find out 2-1 factors, not the real numbers. So here's the 2-1, here's the subfactor, and the subfactor is these things, x is 0, 0. So my question to you is, and we don't go on until you've all solved this, what is the answer? What is the answer? Well, it's the dimension, let's go through it. It's the dimension measured by the small one or the big one. And what was the concept of dimension right from the start of the lecture? How many copies are there of the small one and the big one? Okay, that's the answer. So let's hear it. The answer is, how many copies of R have I written on the board? 4. Thank you. Okay, it's really, it is that naive. That's the answer. Okay, that's basically a proof. So there we go. So now we've got some examples. I think I have a third one here. Oh yes, if we could take, we had this other construction of 2 factors with the groups. So we could take a free group inside another free group, and then we could take L of Fm, therefore inside of this one, just the inclusion of group algebras. Then what do we get here? Well, once again, not many points for guessing. This is the only possible Fn. Okay, and that goes just by coset decomposition, just as you would expect. Each coset gives a copy of the small one inside the big one. Right? So here we've got some index values. And you'll notice one thing about them, right? They're all integers. All integers. This one's always an integer. This one's actually a square of an integer if we vary 2 to the n by n matrices, and the other one is still always an integer. So there's obviously 2 answers here that could be either Murray and Neumann are right, and it's all numbers from 1 to infinity, or the evidence is piling up and it's just the positive integers. Okay, so the question is, which one is it? Which one is it? Well, if I had about 10 more minutes, I would like to give you a very convincing argument that it's the von Neumann result from 1 to infinity. There's a very small gap in that argument which allows the following theorem to be true. Which is that N is in the following set. The answer is that it's neither of those answers are true, and so but both of them are sort of true. So this is the answer. That the index has to be, it has this discrete part, this sort of scattering part, sorry, these bound state parts, and this part, the sort of continuum part. So if you haven't seen the numbers before, let me get them up for you. So 4 cosine squared pi over 3. I don't know whether the incoming undergraduate at Aarhus would be immediately able to say or not. Certainly the incoming undergraduate at Berkeley would not. Anyway, that's 1. Okay. 4 cos squared pi over 4 root 2 is 2. This is 4 cos squared pi over 4. So you'll notice here's the first sort of amazing thing. There is a gap. 1 is allowed, 2 is allowed, and this, 2 is isolated. So if you're actually coming across this as a mathematician, you would spend the rest of your life trying to prove that it was the integer. You've got 1, 2 is a gap between 2 and the next one. Right, well, that's exactly what I did, and I was trying to extend the gap to 3, which is 4 cos squared pi over 6. And I had lots of techniques, well, not lots, but I had a technique, and I couldn't get beyond this value here, which is 4 cos squared pi over 5, which is approximately 2.61803339. Okay, so this is a sort of totally new phenomenon that was coming up. The Fibonacci numbers are embedded densely in the analysis of it, and so then we have 4 cosine squared pi over 7 and so on, and they converge happily up to 4. And then from 4 on, so there's the spectrum, if you like, of the values of the index of a subfactor. Okay, it's all those numbers, and the other assertion, I've only said one direction, which is that it has to be one of these values. It wouldn't be much use if the other direction weren't true, namely that for every one of these values, you get a subfactor. So A and B are all values. There exists, in fact, you can even realize them in the hyperfinite type 2 factor. Okay. So in the probably vain hope that I'll get to the end of all of my topics, let me say there's something a little fake about these values from 4 to 50 here. And that if you impose an irreducibility condition that there's nothing in the centralizer, as you know, in the ring theoretic condition, there's nothing in the centralizer, then this construction doesn't work. And there's still all kinds of mysteries about what's going on for values bigger than 4. Right. Well, now I think I've taken about 35 minutes, and we've got there. I think it's not bad. This was supposed to be a survey talk, so when you give me a survey talk like this, there's two opposing tendencies. One is to be completely indulgent and just go off to turn any little corner you want to and try to entertain and make people understand. Okay? So the bad news is that's what I've been doing for the last 35 minutes. That's the easy part. This is all the stuff that you're supposed to be enjoying and grooving along to. The other tendency, of course, is to inform, to give a survey, to be as comprehensive as possible, tell about all the possible known results, and everyone gets lost. It just becomes a litany of repeated things. And but it's somehow part of the game, right? It's expected of me if I'm doing a survey to actually give a survey. So the survey is going to start now. I'll try to be as gentle as possible by some various devices. So I think we'll absorb this to here. So now begins the survey. So what I want to do is I want to write up on the board 7 different topics, which are areas of interaction between subfactors, other branches of mathematics and physics. It's not a complete list, but it will certainly do it. So 7 topics. And then, once I've written them on the board, I want to go back and say as much as I reasonably can about each one. Okay? Are there any questions, by the way, before I go on? I hope everyone's happy. We've got these 2 factors. They're this abstract mathematical world, they're infinite dimensional Hilbert spaces, and so they have this rather fascinating dichotomy between the index values of subfactors, some sort of meeting point of the discrete and the continuous. Alright, so here's the 7 topics. The first one is statistical mechanics in 2 dimensions. And quantum spin chains. So these interactions, or these topics with interaction with subfactors, I'm going to do them more or less in chronological order. There you have it. The second one is knots, braids and knots in 3-dimensional topology. The third one, I have to respect this chronological order. It's quite useful. There's combinatorics. You might suspect from what I just raised that there is this very big combinatorial flavour going into everything here. The next one is going to be algebra. And of course that's a big topic, so there'll be a small part of it that in particular will be quantum invariant theory. It will evolve. The 5th one will be mathematical physics. There's a certain amount of overlap between these topics, but the interactions I'll be talking about will be different. And here the general world will be sort of algebraic quantum field theory. in infinite dimensional group representations. The adjective infinite dimensional actually refers to the group. 6 will be finite groups. Now these are more recent ones. There's been a rather interesting interaction in the last year or so with finite groups. And the 7th one, the most recent one, that I was heavily involved with is random matrices and free probability. So all of these interactions are significant and ongoing. None of them has cut it out in any way. This, you know, they're all tuning out new stuff. Okay, so I want to start at the beginning and see how far I get. Obviously, the one that I'm most interested in is the most recent one because that's what I'm working on from day to day. But if I don't get there, then it's too bad. So, one thing that's definitely disallowed in a survey talk is to give proofs. So, I'm not going to give any proofs, but on the other hand, in order to get started, in order to see where almost any of these things comes from, I have to at least begin the proof of this result here. Okay, so I'll get back for a little bit to the non-survey spirit. So you see, this result was not so easy. I mean, no one in this audience could possibly have guessed if they hadn't known it before that this was the answer. It came as a surprise to everyone in the field at the time, not least myself. So, how do you do it? I mean, why is it hard, and how do you try to prove it? Well, it's hard because what do you do, you know? You're just given a subfactor and a factor, and nothing else. If you make, you know, way back when, if you made any kind of hypothesis about them, if you said, well, there's some normalizer, some unitaries that normalize the subfactor, or something like that, or something that commutes with it, you would immediately land yourself in the integers. Okay? But you didn't have the integers. You didn't have any. You were just, in the most general situation, given a subfactor of the factor, what can you do? Well, what can you do? Not much, but there is one thing that you can do, and that is this thing about Hilbert space. Hilbert space, these things are like Hilbert spaces. There's not much spare change between these things and Hilbert space. And one thing you can always do with a Hilbert space is whenever you have a closed Hilbert subspace, you can project onto it. Orthogonal projection. That you can do. That's what distinguishes them from Banach spaces. It's a great thing to do. So the first thing to do is to take n, given n and m, you can do nothing else, but you can project onto n. Orthogonal projection. So there you can orthogonally project from n onto n. Okay, it's there, it's a new operator. It's an operator on Hilbert space, it's in the game. So let's just throw it in the game and see what happens. So what do I mean by that? Well, on m, we now have two kinds of operators. One which was really going along all the time I never emphasized, and that was m acting on itself by left multiplication. Okay, that's m itself. It's another way, when you want to represent it, you let it act on itself by left multiplication. So we have that kind of operator, and now we've got another one, which is en, so orthogonal projection. So I'll throw it in and look at the algebra that they generate. So we're going to do that, and we're going to call it m en. And let me suppose this, I'm not really concerned with the infinite index case, so let me, from now on, the rest of the talk, the index will be finite. Okay. So the great thing is, and this is something that couldn't have been discovered by Galois, but because he was too commutative, it's really there in Galois theory. You do this in Galois theory. And what is this? This turns out to be another 2-1 factor. So this is another 2-1 factor. Okay. You could amuse yourself in Galois theory to do this. If this was a field and this was a field, you could do exactly the same thing. There is one of these things. It's called the trace in Galois theory. The same thing. What you find is you get the matrices over the right side over this over n. But we don't have such a simple-minded situation. So this is a 2-1 factor, and it's dual to this one. This is a nice duality, in particular the index of m, en, and m inside this one is equal to the index we started. So we've taken this subfactor, we've thrown it, somehow thrown it inside out and got a bigger one, and it has this information. And also, if you're on the ball, you'll say, well, if it's a 2-1 factor, it has a trace. We have a trace, and we have a distinguished element of the algebra. We have a canonical trace and a distinguished element. So we have numerical information. We have a trace in here. Well, there's not much choice for what this is. It's actually equal to 1 over the index. Can't point to the index because it's between 0 and 1, and the index is bigger than 1. But there's the relationship. So this canonical procedure is throwing in this projection, getting a 2-1 factor, taking a trace. One of the things we can read off is the index. Okay. If I pushed it a little bit further, I could get this gap between 1 and 2. Just by looking at this projection, 1 minus projection. Okay, so this is something that works, and the one thing that I always find in mathematics, it's a lesson that you should learn as a beginning graduate student, but you never learn it. You always have to relearn it every time. When something's working, keep doing it, Keep doing it. Don't stop, because then, you sort of think, oh, well, that works, that's nice, but I prefer this idea here. Then you waste 5 years thinking about that idea there. Then you find you should have gone back and said, oh, but that was working, why didn't I go on? Okay? Well, here we go. Let's go on. We'll do it again. This is nice construction. So now we do the same thing here. We get another one. We get m. This is a horrible notation. Okay, we get another 2-1 factor, and another, and another, and another. Okay, we get a whole tower, infinite tower of 2-1 factors. Each one is obtained from the previous one. We try to fix up the notation. Right now we call this one, all of the other carriers, it's the first one, and we call this one, and the next one will be M, E1, E2, E3, and so on. So the idea is there's this power of 2-1 factors obtained by the second order difference equation, that each one is obtained from the previous two by throwing in the orthogonal projection onto the 1, 2 down. So this one here is obtained from this pair by adding the orthogonal projection from there to there. So you get a tower, 2-1 factors, you get a trace. Remember, there's this trace, this unique trace on all these guys. So you get numerical information. It's all canonical. Canonical numerical information given by the trace, and also you've got a whole lot of things to try to trace out on. E1 words on the ELS. Okay, so this is fantastic. From nothing, which is what we started with, we had just a subfactor of 2-1 factor. We've got an infinite family of projections, and every time we have a word on those projections, there's a number, a real number associated with it, which is given by its trace. I guess it's not very complex, but you can fairly easily see that it's real. Okay, well, normally when you do this kind of thing, the information is boring. In this case, it really isn't boring. Okay. It really isn't boring. And the first thing it allows you to do is prove this result. And that's as far as I'll go in the proof. But now I'm set up to tell you what the interaction was with statistical mechanics of 2 dimensions. Because it turns out you can do some calculations with these EIs. and we find that EI squared, of course, EI squared equals EI, is EI star. That, of course, is just saying that they're projections. But what happens is EI plus or minus 1 EI is equal to tau EI. And otherwise, EI EJ equals EJ EI. The indices are 2 apart. So these are some rules that are satisfied. They're simple computations, just the way things work, basically going back to Murray and von Neumann, or just by doing algebra, or even Galois. This is something that Galois could have done, but the point is that if these were abelian, were commutative, then this one's non-commutative. So because of that, going outside the category wouldn't do it. But anyway, they could have been discovered in Galois theory. These projections, these relations, and they're sort of magic. They allow you to do all of the computations and remember the index. And of course, sadly, they were discovered before. Okay, so I can't claim to have discovered these for the first time. They were discovered by Temple and Lee in 1970. And they form what is now known as the Temple-Lee algebra. I encourage you to go and look at the Temple-Lee algebra and see if you can see these relations in there, and I doubt that you'll find them. But nevertheless, Baxter and others did manage to extract them from that paper and see that they are the key ingredients. So it's called the Temple-Lee algebra. And where did they discover it? They were looking at statistical mechanical models in 2 dimensions. These EIs cropped up as what are called as sort of transfer matrices. What they were doing is they were constructing a lattice in 2 dimensions, and each one of these EIs would actually correspond to adding one of these interactions here between. So this would be E1, and this would be E2, and so on. Add them one row at a time, and you get the so-called transfer matrices of the so-called Potts model. And what they actually did, which is really neat, was that they showed that these transfer matrices, this algebra cropped up in 2 rather different statistical mechanical models, the Potts model and the ice-type model, and they deduced an equivalence, a mathematical equivalence between these 2 models, called Temple-Lee equivalence. Now, I've been plugging in recent years for something a lot more than this. I think that there's another way. There's another way to look at these guys, this tower here, and that is simply, it turns out that these are simply successive, looked at as bimodules. Looked at as bimodules of N. N is a subalgebra of everything, so everything's a bimodule. These are simply these successive tensor powers of M over N. So I'm seeking, to a certain extent I've been somewhat successful, an interpretation of this procedure as building up a one-dimensional quantum spin chain. So each one of these corresponds to adding a quantum spin to each of these. It's not surprising, it's an infinite dimensional object, and there's an equivalence between quantum mechanics in 1 dimension and classical statistical mechanics in 2. So this is the connection with the, this is some kind of deeper explanation, if you like, of the connection with the Temple-Lee algebra. Each one of these, each time you go a step in this tower, you're sort of adding 1 spin to the chain. Right, enough of that. The next interaction was braids and knots in 3-dimensional topology. So what happened here was you can make a braid group representation out of these guys. The braid group is algebraically, it's the group of this presentation. And if you stare at these 2 and look for a little while, you'll see that if you decide to represent braid by TEI minus 1 minus EI, Then if you choose t correctly, let's just say you choose it. If you choose t correctly, then these operators inside this temporally leave algebra, this is the identity, actually represent the break group. These relations are satisfied. So therefore one discovered a host of interesting one-parameter family, at least, of representations of all the break groups, which are somehow coherent with respect to each other, in the sense that if you're in the regime where this index is in a discrete thing, it corresponds to t being e to the 2 pi I over n, plus or minus. The n has something to do with that n over there. So there's these roots of unity, and so these are, since this is an orthogonal projection, these representations are manifestly unitary. So the root of unity times an orthogonal projection minus its orthogonal complement. So they're sort of like reflection groups, complex reflection groups. So there's interesting representation of the Bray group using the trace. One came up with invariance of knots and polynomials, and then that with Witten's input gave some invariance, extended it to 3 manifolds and so on. This is all growing subjects known as sort of CTQM, or perhaps more generally as quantum topology. Okay, so that's an ongoing thing. As a sample of a question that's still open about the original thing, it's not known whether this is the faithful representation of the break group. That's an unknown problem. Of course, some progress has been made by Vaughan in this direction, but I don't really have time to go into the details of that. So, then we go. The next topic of the 7 is combinatorics, and here I want to mention this because there's a Danish mathematician who made a huge contribution. The concept, the combinatorial concept that got out most immediately was that of principal graph. And the principal graph is it's a graph with a distinguished vertex, and it's a bipartite graph. And in order to save time, let me just say in words that the vertices of the graph correspond to bimodules. You take n and m, and you can look at nn bimodules and nm bimodules and mm bimodules and so on. Well, all these vertices have various bimodules, and the edges of the graph, which may be multiple, are just simply restrictions. If you take a bimodule, mn bimodule, and you restrict m to n, then you get a certain number of copies of nm bimodules. Okay, so these vertices are bimodules, and this point of view was really due to Occhiana. But it's a canonical combinatorial object that comes immediately out of the subfactor, and the question is what can it be? What graphs? So this is a finer question than what are the index values, and it's entirely unknown. Well, it's unknown. Lots of examples are known, but there's no handle on answering this question completely, except an index less than 4, where it's known to be the ADE Benjamin diagrams, these are graphs, but not all of them. Only the even D's, and E7 is missing. Okay, and when it's equal to 4, there's some extended classification. But now the question is, all right, what about bigger than 4? What about bigger than 4? I tried to hint in the beginning that there's something still very mysterious about this interval from 4 to infinity, and it was Bisch-Haagerup, I think that's a moderately correct pronunciation, who actually made an amazing discovery, which was that there's a gap between 4 and the next value. And the next value comes along with its graphs, and here they are. He showed that the next principal graphs are these two. There's two that are dual to each other. There's this one, and then there's this one. And what you'll find is that these graphs, the norm squared of the graphs, they tell you adjacency matrix. And you look at this norm. The norm squared is the index of the subfactor, and in this case it's 5 plus root 13 over 2. Okay, so that's what these subfactors, if I wanted to continue this picture, in fact I have to scrub this, because it's a little fake, at least in the finite world. And then the next value would be this Haagerup value, 5 plus root 13 over 2. And then there's another one which is also Haagerup and Osega, 5 plus root 17 over 2. There's some hope for controlling everything up to 3 plus root 3, but then all bets are off. And it's known, in fact, that the classification theory, even of these graphs, is wild. At index 6, you can get the free product of Z mod 2 and Z mod 3 in on the act. That's when things become wild. So there we are. I've used up my hour, and I've got 4 more topics to go, but I'll stop there. And, maybe I say you can learn more about them if you come to my course, because there's an underlying structure called planar algebras, which somehow unifies all of these and gives some new direction to algebra, and that's what I'll be talking about in detail next week in the master class. Okay, thank you.
Stating what you were well known for as an expert, but in fact I'm very happy I didn't try to just throw in a few caricatures in this direction, because you covered it very well yourself, much better than I could say it anyway. So just wanted to start with that route, but then ask questions. Are there any questions? Maybe I can ask you if there was some ideas as to what that special value should be for the hyperfinite ones about 4?
That's about as hard a question as you could possibly ask me. The state of our knowledge is pretty much what I've said. There's between 5 plus root 13, 5 plus root 17, and 3 plus root 3, there is an infinite series of numbers which were recently all excluded. There's one more which exists according to someone's computer, okay, and it's something like 5 plus root 23 over 2, something like that. There's the next one in the series. And the rest of them, all the way up to root 3, there was some promising looking candidates which were sort of looking like these ones. But they all disappeared, and the tool that actually killed them off was that someone showed some, I've been very bad at mentioning names and other contributions here, but sorry. Nixitz and some other people showed that and ultimately Terry Gannon, showed that the index has to be, if the graph is finite, the index has to be a cyclotomic integer. Okay? So, that means using Galois extension iterations. It has to be a cyclotomic integer. And it's also the norm of a graph. So you're looking at graphs that says the norm, at least the norm squared, is a cyclotomic integer. And that turned out to be a huge restriction. And Martin Osega managed to show, doing a bit of very classical 19th century Galois theory, that this potential candidates of Haagerups were actually killed because the norms were not cyclotomic integers. So, beyond that, who knows? There's lots of really exciting looking graphs of examples. Perhaps most of them come from conformal field theory. Work with Feng Shu, he has managed to produce lots of graphs, and Anthony Wasserman. You can get all kinds of complicated graphs, you can get all kinds of interesting properties. You can have an interaction with finite groups and loop group representations. But there's no handle as to what they can do. All you know is that it has to be a integer. One thing that turns out that they're all stars graphs. The distinguished thing, and star has to be on the longest edge. Has to be at the end of the longest edge. And of course, they can also be infinite. There's all kinds of interesting infinite graphs that occur. The Fibonacci graph is an example. That occurs. This is when work with Bisch. You take this graph about, Fibonacci, the thing about breeding rabbits on an island. And if you take the graph of the rabbits that are still alive and how they reproduce and so on, that graph turns out to be the principal graph. But if you try to do, if you just say, give me a graph, then with probability almost 1, I can say that's not a principal graph and prove it. So they're very, very special graphs. And of course, the index values are also very special. The two questions go hand in hand. If you knew the answer to the graph one, you'd know the index one. So, yeah.
So you can do all this stuff. You can start with any old factor and get all these subfactors.
There's another very good question. I was actually quite careful. I wrote here hyperfinite, okay? And I sort of meant it. You can get all these values in hyperfinite. The continuum dies in the hyperfinite if you impose this no centralizer condition. But amazingly, in these ones that look more like the free group ones, it was Popper who showed about 10 years ago that, in fact, this continuum comes back. It's a sort of just staggering result. And in fact, you can get this continuum in the non-hyperfinite case with this irreducibility condition. Okay? And he showed that if you take the free group on infinitely many generators, it's somehow universal. Anything that you can get in any 2-1 factor, you can get in the free group on infinitely many generators. On the other hand, it showed in much more recent work that there are factors, 2-1 factors, only possible values are squares of integers. Every subfactor just looks like a matrix algebra thing. So it's a fascinating question. And this interaction with random matrices at number 7 here, recently I was very happy to discover my own version of Popper's theorem. I can actually construct them in a sort of natural functorial way from planar algebras. I can get all of these continuums in the non-hyperfinite. Planar algebras originally were very hyperfinite, but now there's a non-hyperfinite construction.
Any more questions?